So we started with a linear classifier, and I have, I'm, I have told you that a lot of problems are there with the KNN. So first is like KNN needs a lot of space, then a lot of time while testing, and then again it does not work well for the image. So these are the issues. So again, your KNN is non-parametric approach. That means you don't need any parameter. So parameter is something which is learned by the model. So in the case of KNN, you are not learning anything. Instead, you are just fixing the some hyperparameter. So hyperparameter is your k and the distance metric. That's all. Okay. And you are fully relying on the data because every time whenever testing data is coming, you are just comparing with the all the training samples, and then best match sample will give you the class level. That's all. Now let's go for the linear classifier, which is again parametric approach, where we are going to learn, or your model is going to learn some values, and that is called W. Okay. So whatever we have seen in the previous class, like this W, so this W is going to learn. And then the function is just very simple, that is W into X. So this function you are going to learn. And in this function is fixed, but you are going to learn the values in this W. That's why this W is like magic box. And this is also called weights, parameters in technical, in technical way. And then again, I talk that we need bias also because your model is this W only. So your W may be biased towards some class. Then how to reduce that biasness? So that can be done using bias. So we just add bias so that it will shift the boundary. Because whenever I'm saying W is giving you the boundary of every class. Now I'm going to shift it so that it will be more generalized. Okay. Then we already have talked these all the things. Okay. Then what I told you that we are doing W into X, and let us ignore bias for now, and we are getting the score. Okay. Now this X is like one vector, because whenever you want to apply this W over X, you have to convert your input into vector. So suppose your input is 32 by 32 by 3, then you convert it into vector, that is of 3072 dimensional vector. And now this is your input. So your X would be 3072 into one dimensional vector. Now in this data set, like this is CFAR data set, CFAR 10, so you have 10 different classes. So you are going to get 10 different score. So that means your output should be of dimension 10 into 1. So if that is there, then you can decide, you can fix the size of the W. That would be 10 into 3072. Because then only you will be able to multiply these two elements. Like one is your matrix, one is your vector. Now if you multiply it, it will give you 10 dimensional vector, where in every value is giving the score of the particular class. So maybe this is for the cat, this is for the dog, and so on. Okay. Now, what I said that since in this W, how this multiplication is happening, that we need to see, like we have to just interpret the W. So in the W, if you just carefully see, we have 10 rows. Okay. Because you have 10, first dimension is 10. And every row is having 3072 value. That means we have 3072 columns. Okay. And at a time, if I just see here, at a time, suppose these are the rows in the W. These are the rows in the W. You have total 10 rows. At a time, one row is getting multiplied with the particular row. So suppose first row will go and it will be multiplied with this image, that is your X, and this will give you one value in the output. Similarly, second row will go multiply with the X, it will give you second value. And like that, you will get 10 different values. Now, if you carefully observe here, each row is helping you to get a score of only one class. So first row is responsible for class cat because this is giving a score for the class cat. Second row is responsible for class dog because it is giving the score of the class dog and like that. So every row, in other words, we can say like every row is one template for the particular class. Now this first row is the template of the class cat and it is getting multiplied with the input. So what it is doing, this is just dot product that you're doing. So dot product means what? You are finding the similarity. So if this is highly similar with X, in that case, you'll be getting very high value here. Okay. But suppose this is not matching good with this X, then you'll be getting low value here. So what that means? It means that every template is working as a classifier. So this is classifier for the cat. And this row is trying to get the value or the score of that class. Okay. And if this template of the class has been matched or it's like very similar to X, in that case, you'll get high score. And what that means? That means like this template is saying that this image should belong to the cat class. But again, you have to do this thing for every template, and whichever is giving the highest value, that will give you the class. Suppose if this is giving the highest value, then you'll take the label of this index, like this value, and that is your class. So in that way, it's happening. Now, if I just take every template from here, because we have 10 templates, if I take every template from here and just make the image. So if you just see every template is having how many values? It is having 3072 values. And you have total 10 different templates or 10 different rows. Now this size, the number of columns of every row is matching with the size of the image. That means I can convert this thing into image because this X is also coming from the image. So if I have the same dimension here, I can again go back and I can convert it into image. So this can be converted into 32 by 32 by 3 image. Actually, I want to see what is there in every row. And that's why we are doing this thing. So suppose I have converted it into image. And I have done this thing for every row. And if I visualize it, we are getting this type of images. Now, this is for the first row, this is for the second row, this is for the third row, this is for the fourth row, fifth row, sixth row, seventh, and so on. Now, I know that first row is the template of the plane. And if you carefully see here, this template, this first image is somehow trying to learn the template of or learn the feature of plane. So what it is learning? It's just learning some blue color because like most of the time airplane would be in the sky, so there will be like blue color. So it's learning blue color and maybe trying to learn some structure here. It's not the structure of the plane, but at least it is learning something which is similar to the structure of glass plane. Similarly for the car. Now, if you just see, it's learning the structure of the car along with the color of the car. Now, it's just learning the red color, but in reality, you will be having different colors for the car. So that's why I'm saying like this is the linear classifier. The linear classifier will not do well always. So it can do well for some of the tasks, but for many tasks, you have to do something else also. So along with this linear classifier, you need few more things, and that we'll cover in very detail. So In this way, you can just figure out, or you can just see the, or you can visualize the template of every class, like what is happening inside the W, how it is learning. So this is just a visualization of the W matrix, visualization of every row of the W matrix. Now I assume that this part will be clear to everyone. It's clear to everyone. Okay. Now let's come to the next slide. Here we are just plotting every row, because you know that every row is working as a classifier, because it's giving the classification score of the particular class. First row is giving the score of the class cat, second row is giving the score of the class dog, and so on. So we can also plot the boundary using those values. So if you plot the boundary, you will be getting this type of boundary like this. So you have the template. This is the template. This is the row. You just converted row into image, and this is the template of the car, and you are getting this boundary. Now it's saying that whoever are on this side, those samples will be considered as a car. So we are getting just boundary, like I shown there. No? So you get the, because it's like linear classifier, so it will give boundary. And in every row, from every row, you are getting boundary. One row is giving you boundary of one class. Now this we are plotting for the class car. So just take the values from the first row and plot it. You'll get this thing. That equation, y equal to wx plus b. So you are just plotting this thing. Now this is for class car, similarly for class deer, class airplane, and etc. So in that way, you can also plot the boundary, and you will get to know like how things are getting differentiated. Okay. So these are the template of each class. So this is the template of class airplane, this is the template of class car, this is the template of the class deer. We already have seen these all the things in the previous slide. Okay. Now the question is, when we are not getting right result, or when we are not getting correct result, in that case we'll be unhappy. We'll be not happy with that condition. Now we know that we are unhappy, but how to quantify the unhappiness? Because we have to somehow quantify the unhappiness. We cannot go with binary value like 0, 1. You can say 0 is unhappy, 1 is happy. We cannot go with that. That's not the good way to do. Instead, we have to quantify what is the level of the unhappiness. And the job would be to reduce the unhappiness. So that value should be reduced so that I'll be happy. So our job is to become happy, but for that, first we have to find like what is the level of the unhappiness, and then we have to reduce it. And we will be reducing that value in such a way so that it should reach close to the 0. Because 0 unhappiness means we are happy. So again, we'll do that. And for that, who will help us? Loss function will help us. So loss function is the guy who will quantify this unhappiness. And once you got the unhappiness score, now you have to minimize it. And for the minimization, your optimization will help you. So optimization is the technique which will help you to minimize the unhappiness. And unhappiness we are going to calculate using loss function. So let us dive into that loss function domain. Okay. So let us take few examples. So suppose we have given this image. We have given 3 images. This is cat, this is car, and this is frog. Now you you have given W also. Suppose you got one W. Okay. From where it is coming, that we don't take, that will not focus on that part, because that's not the job here. Okay. Here the job is just find the loss. But again, we'll also see like from where this W will be coming and how to change the W. So everything, all the things will be taken care by your optimization function. Okay, so first see the loss. And for that, let us assume that W is given to you. Suppose I have given you W. Now what I'll do? You will multiply this W with every input. So these are the samples. So this is the first sample. You will be getting the 2D matrix. Then you will be converting it into vector, and then that is your X. You will multiply it, and you will get the score. Let us assume that in this data set we have only 3 classes. Okay. So if you have only 3 classes, that means we need to predict 3 different scores at the end. So that means, like, in other words, I can say like the output size should be of 3 into 1. That is the dimension of the vector. Okay. So do the multiplication W into X, and your W would be what? 3 by 4 matrix. X is, let us assume that X is 4 by 1 matrix, or it could be anything. Maybe it could be like the size of X could be like anything, like maybe original size also, like 32 by 32 by 3. Okay. So whatever the size of the X is, you have to fix those number of columns here, and then it will get, like, you'll multiply these 2 things, and that will give you the score. But at the end, I want only 3 values, because I want the score of every class, and we have only 3 classes. Okay. Suppose you got this score. You did this multiplication, and you got this score for the image 1. Similarly, you'll get the score for the image. Similarly, you'll get the score for the image 3. Okay. Now let us see the first case. In this first case, the actual class of this image was cat, because this is the cat here. Now, after doing this multiplication, your W is saying that this image belongs to car. Why? Because you are getting highest score for the car. That means it's giving the wrong result. It should give highest score for the cat, but it's not giving that. It's giving you highest score for the car. So your W is not doing good for this image. Let's see the second image. In the second image, the level of this image is car. So I should get highest score for the car. Let us check. Yes, we are getting highest score for the car. So this is the happy case, because here, like, we are getting the right result, correct result. Now let's go for the third image. Again, do all the things. You got the score. Now the class of this image is frog. That means we should get highest score for the frog class. Are we getting that? No. We are getting lowest score for the frog. Okay. Now let us see here. This case is unhappy case. This case is also unhappy case. But level of unhappiness is different. Here in this case, at least the score of the cat, that is greater than the score of the frog. It's lesser than the car. That's why this is the wrong result. But at least it is greater than the frog. Now, if you see that this case, this scenario, the score of the frog is lowest score among these all the scores. So if you compare the unhappiness, the level of unhappiness is more here compared to this one. Okay, now that needs to, like, we needs to take care of that. So whenever you are applying loss function, your loss function would give it should give larger value for this compared to this. Okay, so let us start with the first loss function. So we'll go with the simple loss function that is called multiclass SVM loss function. This loss function is very, very easy. Let us see this loss function and then we'll apply here and then we'll get to know like what is the value that we are getting. Now this loss function is having two conditions. One is if and then we have else. So what is saying that if SYI greater than and equal to Sj plus 1. Now whenever I'm saying SYI, YI is the actual class. Okay. So what is saying that if the score of the actual class greater than and equal to the score of other class plus 1, then I'll say that loss is 0. Otherwise, I'll find the loss by this equation. Sj minus the score of the other class minus the score of the actual class plus 1. Let us see here in this case. Now, in this case, the actual class is cat. Okay. So what you'll do? You'll compare this actual class, the score of the actual class with other two classes, the score of other two classes. Let us consider this first. So I'll compare 3.2 is the score of the actual class, that is SYI. And then we have to compare this score with every other classes. So let us first take this class frog. Now greater than 1.7 because score of the frog is minus 1.7 plus 1. Now if you do it, this value is greater than this. That means there is no loss. And this is indeed true, because cat is having larger value compared to frog. So this is fine. There is no problem here. So for this class, you do not have any issue. And that's why you're getting loss equal to 0. Now let us consider the second one. Again, actual class is same only for the selected image. Now we have considered this frog. Now let us consider the car. So actual class is cat, so 3.2 and greater than equal to Sj. So we already have considered this. Now we have to consider this. So 5.1 plus 1. Now this is the problem because this is not true. That means we'll be not having loss equal to 0. So if this is not true, then I'll go for this. I'll find the loss. Like what is the loss? And this loss is very, very simple. Just take the score of the other class, subtract the score of the actual class, and then you just add 1. Okay. Now this is very, very simple equation. Now you could ask the question, why we have considered 1? This is fine. These two things are fine, but why we consider 1? This 1 is called margin. So while comparing, we are also setting the margin. So we want this value greater, but this should be greater. Like the minimum bound is fixed here, so it should be greater than this at least by 1. So this is just for the resolving the trivial condition, because sometimes you can get 0, 0, 0 also. So maybe you are getting 0 here or maybe 0 here. Or maybe sometimes you can get the equal value. Suppose I'm getting 3.2 here and 3.2 here. Now there is confusion. So which one I should choose? Because I know the class should be cat, but for the class cat and class car, in both the cases, the score is same. That is called trivial condition. So in that case, you need some margin. So again, you need the score of the cat highest among these all the scores, but at least larger than one. Okay, so this is generally we use in this funda is coming from the SVM. So generally we set the margin, but this margin can be different. Like you can decide the margin, but in deep learning stuff, most of the time we set margin equal to 1. That works well in practice. Okay. Now you got this thing. If I do this thing, then 3.2 greater than 3.2. Now there is confusion. So your model is saying that loss is 0. If I just ignore this 1, then this is greater than equal to Sj. Now your model is saying that this is fine. Like your loss is saying this is fine. I'll go with loss 0. But that is not true. If you go with loss 0, still you will be in confusion. So there is tie 3.2, 3.2. Like which one I should choose? So I don't want this tie condition. I want this value at least greater than this value by 1. Okay. So that's why this margin is always set, and that is the purpose of this margin. Okay. Okay. So if this part is clear, so let's go for the equivalent part. So whatever I have written here, this can be written by this simple equation. These two are the same thing. So one I have written here in this way, and now I am just replacing this equation with this equation. And both equations are doing the same thing. So here again, you are applying the max function, and this max function between 0, Sj minus Syj plus 1. This part you are taking. So now for every other class, you are checking that whether I have this value negative or positive. If this value is coming negative, then that means you will be getting loss equal to 0. And if this is coming negative, what that means? This will come negative only when you have the score of this actual class larger than the score of the other class. And that is good condition. Okay. So in that case, this value will give you negative, and 0, negative, that will give you 0. Okay. Then this thing again, when you do this thing for the class which is having larger value compared to the actual class, in that case you will be getting positive value because Sj will be having the larger value compared to Syi, because Syi is the score of the actual class and Sj is the score of the other class. Okay. So if you subtract it and if you are getting positive value, that means there is problem. That means you are getting the wrong class. And in other words, I can say like you're getting highest value for wrong class. So this is the same thing. This is the same thing what I have written here, and just doing in a different manner. Okay. And the summation you can see here, the meaning of this summation is like you are going to do this thing for every other class. So for one class, like what I've said that like here you have the actual class is this cat, and you have other two other classes. So you are going to apply this equation for every other class. So first we apply for this or for this, and then we'll apply for the other remaining class. Okay. So in this case, this max function will be applied two times. One for this, one for this. So you are going to first you are going to see the class car, and then you will apply this thing. Your actual class will be same every time, because in this case your actual class is cat only. So your Syi will be same every time. Your Sj is going to change. So first time you are going to take the Sj as a car. So you'll be doing this, you'll be applying this max function over this car, and you'll be getting some value. That is the loss with respect to class car. Now, similarly, you'll be doing for the frog, and that should be added here. So maybe you'll get something 0, or maybe something 8 here, maybe 20 here. Now you'll get 28. This is the total loss of image. This. Let us solve one example. Let us solve one. Let us find the loss for one example. So suppose this is example. So if I write this thing, if I apply max function, so first I will consider this is the actual class, score of the actual class, and first I will consider class car. I want to calculate the loss of cat class with respect to car class. So what I'll do, I'll just apply max function, max of 0, sj is your 5.1 minus actual class is 3.2 plus 1 is your margin. This is with respect to car. Then I'll go for the frog. So the second, so I'll do the addition, then max 0, and the score of the frog class is minus 1.7, and minus the score of the actual class is 3.2 plus 1. Now, if you just simplify it, so you'll get max of 0, 2.9 and max of 0, minus 3.9. Now, in this case, it will give you 2.9 because maximum of 0, 2.9 will give you 2.9. And this case, since maximum value is 0 only, so it will give you 0. So total loss for the image 1 that you are getting is 2.9 using SVM. Now, similar thing you can do for the other images. Now, in this case, since I know that this is the happy case, so if this is happy case, then my loss function should give 0 for this. Okay, so let us see whether we are getting 0 or not. So I can apply the same function. So if I apply the same function, so in this case, what is the actual class? The actual class is car. So this is the score of the actual class. Now you have to apply the max function on all other classes. So let us consider first this class. So max 0, 1.3, the score of this class cat, and minus the score of the actual class, that is 4.9 plus 1. Then for now you will consider this class, the score of this class. So plus max 0, 2.0 minus the score of the actual class is 4.9 plus 1. Now if you simplify it, you will get this. So max 0, minus 2.6 plus max 0, minus 1.9, both will give you 0, 0, and finally it is giving you 0. So in this case, you got loss equal to 0. Now let us see the third scenario. Now, what should we get in the third scenario? What we want to expect in the third scenario? Third is the worst case. It's like level of unhappiness is higher compared to this case. So this should give the higher value compared to this as a loss. So let us see like whether we are getting or not. Yes. So if we go for the third case, your actual class, the score of the actual class is minus 3.1. And now we are going to subtract, you are going to apply this max function for every other class. So suppose let us take the cat class first. So 0 max, 0 max of 0, 2.2 minus of minus 3.1 plus 1. Then max of, then you consider this class. So max of 0, 2.5 minus of minus 3.1 plus 1. So if you just do the simplification, you'll get this. Now maximum value will be come out. So maximum value, I sum it, it's giving you 12.9. So among these all the losses, 12.9 is the highest loss. So now it is quantifying the unhappiness in a proper manner. Now we are happy. So we got whatever we expected to get, that we got. And now the thing would be to minimize it. So what we generally do whenever you are going to train the model, so you'll be not training, or whenever I'm saying training, that means you have to optimize the W. You're going to change the W. Every time you're going to change the values of the W. So if you're going to do that, it is being not done, but it is not being done sample by sample or image by image. What we generally do, we take one set of images at a time, and that is called batch. Okay, so one batch of images will be taken at a time, and those number of images will be given to the W parallelly. And since we have GPU, so we can process it in parallel manner. Okay, so every process will be all these operations will be processed in a parallel manner, and simultaneously we'll be getting loss for every image of the given batch. So suppose these 3 images are given at a time, so we'll be getting loss of all these 3 images. So we got this thing, we got this thing, we got this thing. Now we have to change the W based on this loss, or if I just say in other words, this is just like we have to minimize these all the losses. Okay, so what we do, we sum all the losses and then we find the average of it. So this is like 2.90, 12.9 divided by 3, and this is the average loss, because in a batch we got this as an average loss, and now our goal would be to minimize it. So instead of minimizing one loss or loss of one sample at a time, we generally minimize average loss of n number of samples, that is called batch, at a time. So now this value would be minimized, and its goal should be to fetch this value or to minimize this value in such a way so that it will be reaching close to the 0. Now, if you just implement it, this is very, very easy. Just define this Python function. So this is def, this is the function name that we are giving. It will take x, y, and w. X is your input, y is the actual labels, and w is the matrix, w matrix. And then what you'll do? You'll just you just do the multiplication of w and x. So that is happening here. So again, this is here, like we are using numpy function. So in Python we have numpy, and numpy is like it's very powerful package. So that is giving you all the flexibility for the scientific computation. So it is having a lot of optimized functions which can be used for doing a lot of things for different type of mathematical equation. Okay, so you just take this w dot x. This is the same as w into x. So you'll get the score. Now, what you have to do? You have to apply the loss function. So we are going to apply the SVM loss function. And what is the formula of the loss function? The formula of the loss function is this. So now we have to convert it into the code. So for that, again, we have np.maximum function. So for maximum function, you can just use np. Np is numpy.maximum function. And then we have 0. And then you can write this scores minus score y plus 1. Now, if you just see here, I have not used this initially what I said, that this is happening for every other class separately. But in this case, everything is happening in a single box. So when I'm writing scores, so a score is having 10 different values or 3 different values. Like if you just take the example of previous one, then we have 3 different values, 3 score, like something here, something here, something here. And we also know the score of the actual class. So suppose this is the actual class. So what we are doing, we are just subtracting the score of the actual class from all other class. So this is happening in a single line. So when I'm writing scores, so this is your scores. This is like one vector. And when I'm writing scores of y is your actual class. So it will just take the score of the actual class from this vector, and this will subtract this value from every value which is there in the vector. And then we are adding 1. So it will be added in every. So you, while doing this subtraction, you will get one vector. And then we are adding 1. So this 1 will be added in to every element. Okay. So whatever we have done here, we are just doing that thing through code. Now, there is flaw here. And that flaw is when I say like I have to apply this. So what was like how we have done this thing? We calculated the loss, we computed the loss of other classes. We are not going to calculate the score of the actual classes. Actual classes is the guy. With the help of that guy, we are going to score the loss with respect to other remaining classes. Okay. So what we are doing, when we were applying the loss function, every time we were taking the other classes. So suppose if I apply loss function here, now actual class is cat. So I'm not going to consider this separately. I'll consider first this and then this. So that means I'll be having 2 losses. And then I'll sum it. So every time suppose first time I'm considering this, then I'll subtract 3.2 from this, and then I'll add 1, and then that will give the loss with respect to this class car. Similarly, I will do for the frog, but I'm not going to do the same thing for the cat because cat is the actual class, so that is anyway there. But if you see here in the code, this is also happening for the actual class because you are subtracting the score of the actual class from every other scores, from all the values, and here the score of the actual class is also sitting. So what we do after getting this, we just put 0 for the actual class. So suppose this is the actual class, the margin that we got, like after applying this function, what we got here, that is again vector, and we'll put 0 where we have actual class, and remaining will be C. And then again, the next thing is like you just sum all the things, sum all the values in the vector, and then it can be returned, or maybe you can find the average of it to find the average loss. Okay. Now everything is we got something which can help us to get the loss. Now, what you feel? Do you have some issues here? To add something, is it fine? Are you going to accept it? Definitely, you'll be accepting it. But so do you find that? Yeah, please go ahead.
So just one question. See, by seeing the image, okay, manually we know that this was the class of the cat, so we are not doing any calculation with the cat class. But system, okay, it's going to calculate W on its own, right? He has to improve it. So how he is going to, and machine is going to identify that this is the actual class, and I do not have to do any operation with that.
That we are going to provide. Like this is all the information you are going to provide.
Is it the input? Is it the input one?
Is the input. So that will be set by you, so that your machine will understand it. So there's way to do it. Okay, so there's no issue there. Okay, it can be done very easily. Because while training, you are going to provide samples along with the labels, so that because label like actual.
Please. So what I was saying, okay, see, you took the samples, right? 10 samples in the vector, and then we have got 10 rows, right? First was the cat row, then frog row, right? So the first value which 3.2 came, that came from the first row, right? Which was the training data or the test data, right? So how did the system does not know whether this?
No, this all whatever I'm discussing here, this is only about training data because we are somehow going to train the model. That's why our goal is to reduce the loss.
Okay.
Once your training is done, then your goal is not to reduce the then your model is already expert. Then whatever your model is saying, you accept it. Now, while training, you are going to guide the model so that it will train in a proper manner. It will be trained in a proper manner. So this is like training phase. Okay, once you got the model, then no need to do anything. Just use it, just deploy it somewhere, and people can use it. Loss is only for the training part. Uh, like by seeing this, if I just show you these examples, are you feel that everything is fine, everything is okay, or some changes are required? Just seeing this. If I see you, if I say you like this is the frog, and for this your unhappiness is level of unhappiness is higher, and you got the higher value here compared to this. That is fine now. So do you feel that still some error, not I should not say error, but still some problem is there which can be improved? Or you feel like you can put some contribution here which can again help the loss function? Or everything is good? So again, I'm just asking from you. So anyone can speak and can give the answer.
I think if we multiply it by some constant maybe to each of these figures, then we might be able to tune the losses. Like for example, the score that we are getting like 2.2 or 2.5 or minus 3.1. If we take some, I mean, if we define a constant and deploy, I mean, maybe a value close to 0, then we might be, reducing these scores, and that way the loss function relatively it may not change, but the count, I mean, the difference will go down. I mean, relatively it might remain the same, like because we are multiplying it with the same constant, so relative change will not be there, but
that will come out, na? So if you just apply the loss, it will come out. So if you're multiplying with two factor to every image, then that 2 will come out. So it's like just multiplication of 2. So whatever loss we are getting, that will be like now the loss would be multiplication of 2 of the previous value. So what is the advantage of doing that? Like, are you getting some advantage there?
Sir, here in this loss function, we are not considering the negative value. I think that is getting 0. We are
negative, like minimum loss is 0 means you are happy. Unhappiness is 0. So that's the minimum value.
I'm saying that you are saying na, something if we are missing in this, or you are asking na?
Yeah, yes.
Saying that those negative values we are means we should consider those negative values in some form in the loss, but we are making that 0 directly.
If you go for the negative value again, it will be more challenging for this deep learning network to train it. So that's why like we assume that like we generally stop to the 0 only. So that 0 is like minimum. Now unhappiness, we don't go into negative. So it's like 0. We have reached to the 0 unhappiness. Now it's like we're assuming that this is the happier case or happy case. Okay. So I'll just give you the answer. So actually in this case, we are giving focus on the unhappiness. So every time like I'm saying like, yes, here this we are getting, and this is like unhappy case, and we are getting a score for this. Even for this also. Now this is more unhappy case, then we are getting even more values here. But our attention is not on the happy case. So even in the happy case, if this is just touching the margin, I'm saying that loss is 0. This is just like when suppose your child or maybe someone is getting 40 marks, this 100 marks exam, if he is getting 40 marks, and then 40 marks is the passing mark, then what I'm saying, like he got the 40 marks, now his loss is 0. Now we are happy with him since he has touched the margin. Now, whether he's getting 60 marks, 50 marks, 70 marks, in every case, we'll be saying that loss equal to 0. So just touching the margin, we are saying that loss equal to 0. But in real scenario, we'll be not happy just touching the margin. Suppose your child is getting 40 marks, you'll be not happy. Most of the parents will be not happy. They want their child to get marks close to 100. So wherever like he's getting 40, 50, in every case, their parent will penalize them. But that level of the penalization will be different. So suppose if their child is getting 40 marks, they will scold them. Maybe level of a scold will be very high. If their children is getting maybe 60 marks, then the penalization will be lesser. If their children is getting 80 marks, then their parent might be happy and maybe will giving only some punishment. So punishment level is getting decreased by increasing the marks or by getting the marks like higher marks. Only the saturation point is 100. So once his child got 100 marks, they will not penalize them or they will not punish them. Okay, so this is the general scenario, and it's also applicable for this type of loss function or this type of deep learning type of optimization. So here also we are not only happy with just margin. Now here it's just touching the margin, we are happy. Now we are not quantifying the happiness. So we have to somehow also quantify the happier case. So we'll be only happy, 100% happy when it will be reaching to the highest value that I wanted to get from this. So for that, softmax came into the picture. So softmax is the guy or is the algorithm which will give you that type of flexibility. So let us see the softmax. And once we complete, then you could ask questions also. So again, we start with the score. So this is the initial part, just like SVM. Now, as your SVM was working on this for finding the loss, now your softmax will not do that. Instead, softmax will apply multiple steps before calculating the loss. So what softmax does, first it will find, its goal is to find the probability value, or its goal is to convert all the scope into probability values. So what is being done? First, it will apply exponential function so that all the negative values will be converted into positive values. So if you apply exponential function, every value will be positive after this. Now your job is not done because probability says that every value will be positive. That is true here. But the second condition is that every value should be between 0 and 1. And if you sum it, all the values, that will give you 1. So that is not happening here. So how to do it? Just normalize it. So next part is normalization. So sum all the values here and divide that value from every value here. So divide by sum, divide by sum, divide by sum. And now you got the probability values. So now if you see here, every value is coming between 0 and 1. And if you sum all the values, that will give you 1. Okay. Now, we started from here and we reached to this point. Now, if I ask you, what is the goal here? What should we do with this? Should I minimize it or I should maximize it?
Maximize it.
To maximize it, the maximum value is 1. So I have to reach to the 1. Okay, and if I'm going to the 1, if I'm reaching to the 1, that means I'm fully confident that this image belongs to the cat, because for cat I'm getting 1. And if you are getting 1 for this, what will happen for others?
0.
They will reach to the 0. So just applying this loss function on one value, we don't need to apply this function on other values, because that is happening automatically. So in the case of SVM, we were applying the loss function for every other class, which is not required here. If I just apply this optimization on this, that will solve the problem, because all these values are related. If I'm increasing this, at the same time, this will decrease. This will decrease. That was not happening in the case of SVM. So that's why we were treating every other class separately with respect to the actual class. Here, just considering the actual class, all other class will be they will be taken care automatically. Okay, so our goal is to reach to 1. That's fine. Now, what is this problem? This is called maximization problem, because you have to maximize the value. You have to maximize this 0.3 to 1. Now, what I've seen that in the previous loss function, that we want to minimize, like most of the time we solve problem as a minimization problem. So we also want to convert this problem into minimization problem. This is now maximization problem, but I'm not interested in maximization problem. I'm interested in the minimization problem. So what I'll do, let us do something to convert it into the maximization problem, minimization problem. So can I take log of 0.3? If I take log of 0.3, do you feel that this maximization will be converted into some other things, or still I have to maximize it? Still I have to maximize it. Log will not change anything. It will just change the value. The problem, the type of problem is remains same. So this was like here, like just our goal was to maximize it. Now for the simplicity, for simplifying it, because most of the time we apply log, because log gives a lot of things, lot of other things which can make the process easy. So I just apply log of this. If I apply log of this, there would be no change in the problem statement. Still, this is maximization problem. Okay, you have to maximize this log of 0.3. Now, can I convert this thing into minimization problem? Can I say like maximization of 0.13 is equivalent to minimization of 1 by 0.13? Basic math. Because your maximum value is 1. So if you're maximizing the 0.3 here, 0.13 here, that means you are minimizing the 1 by 0.13. And this is same as log of 0.13 this. And you know that if you log this thing, minus can come outside. This is as minus log 0.13. Are you able to understand this part? So what we have done, we have converted the maximization problem into the minimization problem. So initially we have to maximize it, but now we applied the log, and then we took the negative of this log. This is minimization. So this value should be minimized. So let us see how it is happening. So if it is coming 1, What value will be getting from here? Minus of log of 1. That will give you 0. So we are on the right side, because when this is highly confident, that means this is 100% confident, then your loss is 0, because others are like 0, 0 only. Your loss is giving the same thing. It means it is doing the good. It's doing good. Now let's see when this is 0. If this is 0, then log of 0 would be infinity. Like maybe minus. So you'll get infinity here. So when we are taking 0, then you are getting infinity, and this infinity should be minimized. Okay, so this is like unhappiest condition when for the actual class you are getting 0 probability. So in that case, your loss should be very high, and that is happening here. And all other values will be between 0 and 1. So that means like you start from the infinity loss when you have 0 probability for the actual class, and then your goal is to reach to the loss 0. At that time, you will be having 1 probability for that. And that's the actual goal. And the same thing is happening. That means your loss is helping you. If this is clear, then. Okay. So the same thing we have done. So minus of log 0. This is the score. This is the loss that you are getting using the softmax, and this loss should be minimized. So this should go close to the 0. That should be the goal. So we have converted the maximization problem into the minimization problem. Now, let me just tell you, maybe you might have heard this name before. This formula that you are seeing here, this is called cross entropy. Have you heard the name of entropy before, or cross entropy before? Entropy, if I just say entropy is like randomness of the system. How random your system is. So suppose if my system is like, I'm saying that this guy, maybe I just consider this Virat Kohli. Okay, so if I say like Virat Kohli will hit century in, or maybe I take Shubham Gill. So if I say like Shubham Gill will hit century in the next match. Now, like how much information I'm getting from here, from that sentence? Like we know that Shubham Gill is in the form, and there is like, it's like we have, it's like high probability is there that Shubham Gill will hit century in the next match. So there's no much information that you are getting from that. So if that is the case, that means your entropy is low. So whenever I'm saying entropy will give you the information from the system. So this is the system. But I'm asking like whether this guy will hit century in the next match or not. Now, since you know that the guy is performing well in every match, so there is like more chances that he will hit the century in the next match. So you are not getting much information from that. So that's why your entropy is low. So whenever you have high probability of occurring the particular event, your entropy will be low. But if I say like Kenya wins the World Cup, and Kenya wins the World Cup next year, now there is a rare chance of occurring this event. You know that Kenya cannot win. But suppose this happens. If it happens, then everywhere, like in all media, this news will come. That means we'll be getting a lot of information. Because the thing was that we are assuming that this will not happen. But if this happens, Whenever the occurrence of particular event is, the probability of occurrence of particular event is very low, in that case, your entropy will be very high because that is the special case. Okay. Now, that is called entropy. Now we have cross entropy. So whenever I'm saying cross entropy, it means there is two systems involved here, or there is two distribution involved here. So in the entropy, there is only one distribution or only one system is involved there. You're just finding the this entropy for the particular system or particular distribution. Maybe I should say distribution is like a set of probability values. For example, if I say like what is the distribution of this this tossing the coins, then you can say like the distribution will be head and tail. So these are like this is the distribution. Either you will get head or you will get tail. And probability of head is 1/2, probability of tail is 1/2. So that is your distribution, or that is like one system. Now, if I say cross entropy, that means there is involvement of two systems. Now, I say that this is cross entropy. Now, just looking this, it's not looking like a cross entropy because we have only one value involved here, and this value is coming from the prediction. So prediction is again one distribution because you are getting all the probability values here. And the set of probability values is like that is called as a distribution. So we have a set of probability values and that we are taking from there. So one distribution is there, but where is the second distribution? Why we are calling this as a cross entropy? So second distribution is also there, but it is invisible. So how it is happening? This is your predicted distribution, probability distribution that you are getting, and you have the actual distribution. So if I write here, you are getting this 0.13, 0.87, and 0.00. But in advance, you also know what is the actual probability distribution, and that is your ground truth. So if you just see the ground truth is saying that this is cat. That means one probability is given to the cat and remaining are 0. Now this is your actual distribution or your ground truth distribution, and this is the distribution, or these are the values that you are getting from the model. Now this formula is being applied between these two. Okay, so how it is happening? It is just like minus of the distribution of minus of first distribution, that is this 1, 0, 0, log of second distribution, that is this 0.13, 0.87, and 0.000. Now, if you simplify it, you'll do the element wise these operations. Then these two parts will go because we have 0 multiply with this log of something, that will again make 0. This will also make 0. Only the first part will be left. And what is that first part? It is minus of 1 log 0.13. And this thing can be written as a minus of log 0.1. So this 1 is there, but that is not required. So that's why it's not visible there. So actually we are applying this cross entropy. And this is widely used loss function in the case of deep learning. So most of the time, whenever you are solving the classification problem, you will be using the cross entropy. And that is based on the softmax. And that's why we say softmax classifier based loss function. Okay. So this is the same thing that I've discussed. So this log is there, multiply. So only these values will remain. Log is this side. Sorry, I should not write in that way. I think I already have explained these things. So this is your actual probability. This is the probability values that you are getting from the model, and then you have to apply the cross entropy. That is like minus of this log this. Okay, so we have seen two loss functions. One is SVM. That is again max based function. We just apply the max function and we get. So let's see the full pipeline. So we have W, we have X. You multiply it, add the bias. Now, now actual class is 2. That means this is the actual class. So 0, 1, 2. So if I apply SVM loss, what I'll do, I'll subtract the value of this class from other classes. So max of 0, first I will take this. So minus 28 minus 0.8 plus 1 plus max of 0, 0.86 minus 0.28 plus 1. Now if you just simplify it, you will get this. Similarly, I'll go for the cross entropy. So I got the score, apply the exponential, normalize it to get the probability values, and then choose the probability of the actual class. So this is the actual class, and then take the minus log of this score, and that will give you the probability. That will give you the loss using this cross entropy. So you can apply like, it just depends on the problem statement that you are solving. So most of the time, if you are solving the classification problem, you should go with the cross entropy. For some other type of problems, hinge loss can be also used, like for the maybe for regression problem, or maybe some different, even classification also you can use. But this cross entropy loss is like widely popular, and you have seen that this is also giving some weightage to the happiest side, which was missing in this case. Okay, so with that, like I'll stop here. So in the next class, we'll cover this regularization and optimization. So you could ask question if you have any question till now. You could ask.
Sir, after defining the loss, what we will do with that? Like how the next time the weightage we need to rearrange, right? We need to do something with the weightage also according to the loss that we are getting, right?
No, you're talking about what, like this
So
to get the
calculated. We have calculated. So see, we are trying to classify with the help of weightage into the classification matrix, right? So suppose that it is giving the wrong value and the loss function is there. So we need to weightage. We need to do some changes, right? According to whatever.
Yeah, you got the loss, and that loss should be minimized. That is the goal.
Yeah.
So for that we have algorithm. So again, so that's what I'm saying. Like we'll be going through this optimization. So optimization will take care of this thing.
Next class.
Yeah, you have to wait for the next class.
Okay, sir.
Sir, so just to clarify my confusion, so this loss function and activation functions are all same kind of thing?
No, activation functions are different. Activation function we'll see. That is also called non-linear function. So the goal of activation function is different. The goal of the loss function is to quantify the unhappiness, and then you'll be using optimization to minimize it. But the goal of the activation function is like to put non-linearity in the system. So again, that will come later.
Okay, fine. Sir. So apart from SVM and Softmax, there are other loss functions are available also? Or
a huge number of loss functions are available.
Okay.
These are like some common loss functions, so that's why I put here. But you can study about all other loss functions also. Even if you're solving the regression problem, then you could be having like L1 loss function. L1 can be also used as a loss function. L2 also can be used. Like this is just like mean square error. That is also error. So for this classification problem, these are like suitable. But for other type of problems like regression problem, you could be using different type of loss function, which are suitable for those type of problem statements.
So is there any specific way that what should we use when, or we need to just do trial and error that wherever we're getting the better result, we should use that one?
A lot of previous papers are there. So just seeing all the previous papers, you will get to know like which are the loss functions that give more accurate result in practice. So that can be seen from the previous work. Based on the
Okay.
experience, also you'll get to know like which are the loss function I should use. But in practice, like if you are solving, what I observe that if you're solving classification problem, most of the time people use softmax or variant of the softmax, or very like I should not say softmax, like cross entropy. So cross entropy or variant of the cross entropy, or you might get some other also. So you can try, like it's just trial and error. So you may try a lot of loss functions which are suitable for the classification. Before that, what you guys can do, you can also explore like PyTorch. PyTorch tutorial, that is like, again, it's like very good documentation there. So it's like every line is explained in a proper manner. So just go through that. So you'll get to like they have made the model, classification model, just line by line, and it's like maybe 100 lines code. You just go through that, and you can also run that code in Google Colab. So that will give you some initial understanding, and later if it is required, definitely we'll do something. We'll try to give.
Sure.
Demos.
Thank you.
Yeah.
Question I have.
Yeah,
So
please.
why are the values negative in this like xi? So these are image pixels, right?
Yes, your question is valid, but we are assuming this is just hypothetical image. So here we are also allowing negative values, but in reality, when you are dealing with the actual image, then in most of the cases you will be having positive value only. But yes, let me just tell you, sometimes we could be having negative values also, because suppose you are working on the image, but we are not directly giving image to the model. Instead, what we do, like we convert into numerical values, then we also do some type of normalization on the image also. So like you can do some normalization like mean, mean, what we say, like a lot of normalization techniques are there. So some normalization technique can make or can push all the values between some range, or like it maybe between -1 to 1. So in that case, you could be having some negative values also. So this is again based on the normalization technique that you are using. So negative values will be also there due to the normalization technique. Okay, so what I said that whenever you are working on the image now, sometimes like we also do some normalization. So we are not giving image directly to the model, or those values directly to the model. Instead, what we do, we just do some normalization. We normalize it in some range. So maybe if you take a range between -1 to 1, like mean 0. So in that case, you could be having some negative values, some positive values. So that is possible. That was like negative is also possible.
Got it, sir.
But this is just hypothetical image that I put here. This is not the actual image. This is just for the example, just showing this whole process, how it is happening. Any
Hi,
other
sir.
question?
How do we calculate this W, sir? Do we have any formula?
That is W is the magic box. Actually, this whole, like, we'll be having 2-3 more lectures only about this W. So we'll be giving a lot of time for this W, how to calculate, who will give you. But for now, let us assume that God has given to you this W, and we're just using this. But again, this is big game. So this is again big domain, because anyway, like we are going to optimize this W only, because W is playing this magic. So whatever you are getting, that is coming from the W only.
Yeah.
Okay, so again, so that's why we have to optimize it. So we'll do this thing. We have a lot of algorithms for doing this.
So for now,
We
it
invest a
will
lot.
be in the, for now it will
For
be in
now-
the problem.
Yeah, what?
For now, it will be given in the problem. this input for W.
Yeah. For now, we are assuming that this W is given to us.
Okay.
For now, the goal is to just find the loss, how good your W is doing. Later, we'll if we are not, since we are not happy with W, then we have to change the W. Maybe we'll choose some other W, or maybe we'll do some optimization. We'll apply some algorithm which will optimize the W so that next time it will give you lesser loss compared to the current. So these all things we'll be seeing.
So we are not aware of the deciding factor for the W for those classes.
For this, we are just somebody has given W to you, and you are just seeing like how good your W is, or whatever W he has given, how good that W is. That's all.
Okay.
And that we are going to calculate using loss function. So your loss function is giving that information, like how good or how bad your W is.
Okay. Yeah. Got it, sir.
Yes.
Sir, in the cross entropy loss, you considered 1, 0, 0, that is column matrix, and you multiplied that with the log of the loss that we have calculated. How did we have it 1, 0, 0, sir, there? That's a known value.
What? That is known. So whenever I'm saying that this image, and this belongs to cat, then I'm 100% certain that this is cat. So I'm giving 1 here, 0 here, 0 here. Okay. So if no further question, then I'll stop here. And in the next class, we'll see the two of the things. One is like a regularization, and then we'll go for the optimization.
Thank you.